All right, so today I'm going to talk about hypothesis testing. I don't know that this is going to take the entire rest of the time. Who cares? We don't care. It probably will, but if it doesn't, that's also fine. I want you to know the stuff. If you feel like you need to know more things, I can teach you extra stuff. Nobody ever feels that way. Okay, so I'm going to talk about hypothesis testing today, and there's three things we need to say if we're going to say we have a causal relationship. And that's what we want to do, right? We want to be able to get some data and say, look, here is a causal relationship. We know that X causes Y. That's what we want to know. Okay? So the first thing you need is temporal precedence, meaning the cause has to come before the effect. That's just the way the universe works. Causes come before effects, unless time's going backwards. So it's not supposed to happen unless we have a big crunch. So, which will be billions of years after we all die. So let's not worry about time going backwards. Time has to go forward, so the cause effect, right? So that's the first thing we need. We have to eliminate alternative explanations. Well, that's one you can often solve with design, right? So if you think about let's think about a simple experiment where I divide the class into three, so 3 equal groups, and I give one group 0 drinks of alcohol, I give one group 3 drinks of alcohol, and I give one group 5 drinks of alcohol. And then I test your memory. And I find the group that drank the most had the poorest memory. However, there is a very simple alternative explanation for this. What is it? What's the alternative explanation? I mean, there are probably others, but I can think of a pretty simple one.
No relation?
No, let's say we found a relationship.
Okay.
Yeah. But let's say it's not the alcohol. Let's pretend it's not the alcohol. By the way, it's the alcohol. But what's another explanation I can have? Because I designed a shitty experiment. What's another explanation?
The other groups are caffeinated.
Caffeinated? No, I didn't say I put anything else in anybody's drink.
The people who drink the lowest amount of alcohol have the better memory.
No, they're gonna have the worst memory. They do. They will, and B, let's pretend that's the results they got. So the 5 has the worst score, 3 is the best, is middle, and 0 drinks is the best score.
Yeah, that's what I
Oh
meant.
yeah, that's true. That's what we should get.
Okay.
But let's say it's not the alcohol. Well, it is the alcohol. But the way I've designed this shitty experiment is that I can't tell you it's the alcohol. I have an alternative explanation in my head.
The people that had the most alcohol just have worse memory.
Yeah, let's say we randomly assign people to groups, so we have to worry about that.
Is the alcohol drinks not alcoholic?
Oh, they're alcoholic. They're gonna be vodka tonic. Vodka and tonic. Just vodka and tonic. Or vodka and soda, just straight up vodka and soda. Don't you think the people who have had 3 drinks, or sorry, the people who have had 5 drinks, just drinks of liquid, have to pee? People who have to pee don't remember things as well because they're going to pee. Well, what we could do to fix that. So that's an alternative explanation. It's wrong, by the way. It's the alcohol that's doing it. It's not that people have to take a piss. But we want to eliminate that explanation. So in that case, what we would do is we would give everybody 5 drinks. One group has 0 alcoholic drinks. One group has 3 alcoholic drinks. One group has 5 alcoholic drinks. They all have 5 drinks. And you might say, Dave, what about the flavor of the alcohol? That'll tell people what group they're in. Not if you put enough peppermint oil in it. Enough peppermint, people can't taste the alcohol. That's how these things are typically done. A really heavy flavor masking agent like that, and just soda and vodka is typically what's used, because it's flavorless.
Oh, you feel better.
But if you can't taste the vodka, because you can't taste the alcohol, because there's so much peppermint. Turns out, by the way, that people in these experiments actually do show a placebo effect. They think they're drunk. When I was in a postdoc, a friend of mine ran experiments like this, and she was testing the effects of alcohol on people's, a bunch of perceptions and things, I don't know. I was never in one of the experiments. But if you signed up, the first thing she did is she took your car keys, and then you were given your drinks. You were told the group you're in, you're given your drinks, and then you did your perceptual task, and then you were told you get your keys back when you blow below the legal limit, because she had a breathalyzer. Now the control group, who all thought they were under the influence of alcohol, were told, you're the control group. And she said, very typically, people go, no, they're not, I'm drunk. And blow this, and it blows a 0. They go, oh, I feel fine now. So there actually are real placebo effects there. And that's how you do that kind of experiment. We have now eliminated the alternative explanation of people have to take a pee. And 5 drinks, actually, when you think about it, if there are 5 actual like highball glass drinks, you would have to pee. I mean, I would anyway. Of course, I'm old. And covariation, obviously. So we have to know that as A changes, B changes. As number of drinks change, memory performance changes, that kind of thing. So that's temporal precedence. That's covariation. Now, we can get at the first two with design, and I've been talking about design. Right? Research design, like, 2127, 3286, that stuff, the boring stuff that everybody hates. 3286 probably isn't that bad, but that 2127, I think I fell asleep once giving a lecture. It was so boring. I haven't had to teach that class since 1997, and it makes me incredibly happy. Because it's just, you have to know it. It's really important that you know it, and it's really important that you don't hear it from me, because I would be bored stiff. You know me, I try to make it fun. Oh, isn't this exciting? Let's talk about random assignment of subjects to groups. I don't know. All right. All I'm saying is it's boring. So, we can do these first two, though. This is why you actually need those courses, right? As boring as they are, they're important, because if we're going to say that one thing causes another thing, we have to find these things. And these first two are about design. This is about covariation. That's going to be about statistics. Now, I'm going to show you some numbers. These numbers are just, I don't know what they are. I made up 2 sets of numbers. They're just 2 batches of numbers. I don't know what they are. Don't ask me. Make up your own example. There's 2 groups. One group has a mean of 66 and a standard deviation of 785. Another group has a mean of 71.6 and a standard deviation of 856. 8.56. Okay. The numbers themselves aren't super important. Really, the means and standard deviations are going to be more important. So if you think it's important to write down the numbers, fine. I'll just stand here and keep rambling for a little bit, but it really isn't. Okay. So that's 2 groups, and of course we're going to try to determine if group 1 and group 2 are different. So are they actually different, right? So here's the question I'm going to ask you, and that's, well, first of all, let's take a look at this distribution. This has a mean of 72, and I forget what the variance is that I put in there. Now you see why the notes do that. Okay, so could these 2 sets of scores come from this same distribution? This one here. This looks like it has a mean of 72 and a variance or some deviation probably looks like about 6. So I'm just pretending that I know the population distribution for this variable. I don't. You never do. This is all theoretical. You never know this. If you know population values, you don't have to do experiments. Like you don't have to underestimate this. You don't have to estimate it if you know it. That's why you don't do experiments on populations, because you don't have to. But in this case, we got 2 groups, and what are those 2 standard 2 means again? So I told you it matter that I'm asking you what they were.
66.2 and 71.6.
Okay, 66.2 is here, 70. Oh boy. Holy jumping. It seems like this is probability, right? This is of something happening. Oh boy. That's it really looks like both those sets of scores could come from that distribution. So what this is saying is that group 1 comes all from that distribution, as does group 2. So if that's the case, the groups are not different. They come from the same population, the same place. They're different because as we randomly select observations, everybody's different a little bit. Like if I just took this classroom and I randomly selected 10 of you and got your height, and then I did it again, I'd get two different heights, two different averages, wouldn't I? Unless I randomly selected the same 10 people. And there's how many people here? So there's 18 people here, so what's the probability of me getting the same one? That's, 1 over 10, so let's do 10 to 10 choose 2. 1 over 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3. It's really unlikely that I get the same number, the same people. It can happen, just unlikely. And that's in that smaller group. You see, that's really something, isn't it? Right? So it's just 10 choose 2 if you know combinatorics. So what I'm saying here is that we didn't get the same two sets of people each time. We can't have. But we would have definitely got different numbers for mean and variance, right? But they come from the same population, considering you guys a population. That can happen. Of course it can. So in this case, and this is a completely, I don't even, like I said, I don't know what the numbers are. I don't know why I picked those numbers. You know, I might know, but none of you be interested, so I'm just gonna let that go. Yeah, that's neat. That's what. Okay, I'm going to tell you. Those actual numbers come from when I was the first time I taught a research methods class, the boring stuff at Western when I was a postdoc. I was given some old notes by somebody, and I think those are the numbers he used. And that guy ended up being my daughter's PhD advisor 30 years later, which is weird. Anyway, the point is that they come from the same place, quite possibly. We don't know this. We never know this. We don't know populations in advance. If we did, we wouldn't have to do this. But does everybody see what I'm saying here? That it's pretty likely they both come from this weird similar parent population distribution. Okay? All right. So we just made a decision. We just said the chance is relatively small that these things come from the same distribution. And if they don't come from the same place, they come from somewhere else. Right? They're mutually exclusive categories. They're either the same or they're not. They can't be kind of the same, right? So we've made a statistical decision. And we usually make decisions saying that if it's pretty unlikely they come from the same distribution, then we say they come from somewhere else. And the number we usually use is 0.05. There's a 5% chance. Because it's certainly possible. It's certainly possible that two things can not come from the same place, and it looks like they do. It's just it's unlikely. And we basically said we're going to say 5%, 1 time out of 20. You're going to hear a whole lot very soon because of the looming federal election. You're going to hear political poll numbers, and you're going to constantly hear this. This poll is accurate plus or minus 2.5 percentage points 19 times out of 20. 19 times out of 20 means 0.05, doesn't it? 19 times out of 20 is 0.05. There's a reason they're telling you the margin of error and the confidence, the size of the confidence interval, which is kind of neat. So you're going to hear people during an election say, well, I guess that's the 1 time out of 20 it's wrong. And please, that's not how it works. It's not that every 20th poll is wrong. You know that. It's not like that every 20th experiment is wrong. It's the chance of this experiment me having misinterpreted this and saying they're from different groups and they're from the same group is about 1 out of 20. And because we're probably not curing cancer here, we're okay with that. That's close enough. We may want to adjust that. We'll talk about that as we go. But we usually use 0.05, which is ridiculous. It's completely stupid and ridiculous that we arbitrarily draw a line at 5% and go, yep, right there. More on that later. So without statistical significance, which is what we're talking about here, we then say we do not have covariation. Therefore, X does not cause Y. So as much as we've dealt with the other stuff with temporal precedence and with elimination of alternative explanations using design, this we're using statistics. Why is there a piano here? I mean, why not? Is the other question, right? Like, because there's no reason for it should not be here, but it just strikes me odd. Anyway, I used to. My dad had a company that made flight cases. That's what I was looking at. My dad owned a music store. I grew up with stuff like that. I thought it was normal to have like 30 electric guitars in your house and a basement full of amps. Yep.
So why 5% exactly?
Oh, we'll get there. It's completely arbitrary and total bullshit. But we will get there. We'll get there in about 10 minutes. It's a great question. And you're going to be, you might be surprised, you might not be surprised. It's hard to say about, like I said, it's completely arbitrary, and I think you'll find it kind of funny why it's 0.05. So what we do is we set up two mutually exclusive hypotheses. Whoops. Wrong button, you idiot. Okay, I was talking to myself there, by the way. Okay. We set up HO, or the null hypothesis, or as it was called before this became a term, HO. Remember in undergrad, people would say HO and HA. No one says HO anymore because they're, you know. Or HA, sometimes H1, you'll see that too, as the alternative hypothesis. H1 and HA are the same. Like, there's nothing wrong, there's different notations, okay? So we just set up these two hypotheses. This says there's nothing happened, this says something happened. This says they come from the same distribution, this says they come from different distributions. All those things I just said mean exactly the same thing. Okay. So the null hypothesis, or HO, or hope, is that nothing happened. The groups of scores all come from the same population distribution. Okay. Ha, the alternative hypothesis, or H sub 1, sometimes, or H sub A, says that they do not come from the same population. They are not the same. It doesn't say which populations they come from. It just says they don't come from the same one. That's an important distinction, by the way. So when you find that HO isn't true, because you've set up two mutually exclusive hypotheses, we then, through inference, just go, well, then there's only one left that could be true. Okay? So the logic of this is that if this isn't true, this is the only thing left. But the important point here is we never say we accept HO. We never say, therefore, that is true. We just say we reject the null hypothesis. It's not true. And it's left up to everyone else to go, well, there's only one thing that could be true. Because there are other weird possibilities here. Okay. What we've done here is we've set up what's called a straw man, right? Like if you ever think about sort of argumentation, right, in like philosophy, setting up a straw man argument. That's what you've done here. You've set up a straw man. You've said, we want this not to be true. We want the null to not be true because we don't do experiments hoping to find nothing. You do experiments hoping to find nothing, you don't find anything, you publish nothing, and eventually you don't have a job anymore. That's how it works, okay? Okay, so you've probably seen a diagram like this before. I think there's one in the book. Errors and hypotheses. We're obviously going to make mistakes. Now there is reality, HO true and HA true. We don't know it. We cannot know it. If we knew it, we wouldn't do the experiment. Right? So if we knew reality, if we knew that HO or HA is true, why would we do the experiment? Right? After an election, and they've actually counted all the votes, they don't go, well, let's do a poll just to be sure. No, you've actually counted the votes. You've got that population. So that is something, that's reality. Then here we have our statistical choices. Don't reject HO or reject HO. Note it does not say accept anything. It says reject or don't reject. Okay. So let's do that for a sec. So a correct decision. We do not reject HO when HO is true. So instead of making it about alcohol and memory, let's make it something that perhaps you'll feel a little bit more, what's the word I'm looking for? Affinity for, or you'll understand a bit better, or it'll be more fit with your life experiences. Pregnancy tests. I think everybody in here, or most of us, have experience with pregnancy tests. You're not pregnant, and you don't get piss on the thing. It doesn't have any change color. I can't remember. I haven't seen a pregnancy test in 31 years. But and depending on where you are in your life, or aw, this is a scary one, right? It's not super scary because we'll find it eventually. But you're HO, you're not pregnant. This says you are pregnant. It's type 1 error. I found a difference, but there isn't one. I'm pregnant. No, you're not. You find out pretty quickly if you're actually not pregnant because you have a period, right? It's like, well, I guess I'm not pregnant. And a lot of people, what they do is they'll take another test. I know a lot of people buy 2 tests. Like, let's do a couple just to be sure. But that's an error. That's a mistake. Now, what about this one? This one's a weird one. You don't want to say, like in print, let's say instead of pregnancy, it was like, there are psychics, was your, well, ended up, the result would be your alternative hypothesis. If you say that, you should be an idiot of yourself, so you better be goddamn sure you're right. Okay? The problem here with a type 2 error is, well, you might miss something. And again, with the pregnancy test example, well, you'll find out eventually that you're pregnant. Oh, I'm not pregnant. And then like 2 months later, you go, I haven't had any periods, and I'm kind of putting on weight. Maybe you are pregnant then, right? That's a type 2 error. That's the probability of failing to reject a false null hypothesis. And you should be able to tell that just by looking at this matrix. Or what if there actually are psychics and you missed it? Ah, damn. Well, at least in the grand scheme of science, someone will find it someday. Just you blew it and you don't get your Nobel Prize. And then there's this one, the one we all want, which is correct decision about there being an effect. And this is the one that when you want to have a baby, it says, yay, look, we're pregnant, yay. And you can call your parents and say nice things. I remember I called my dad and I said, hey, Dad, what do you want to be called? Like what, Grandpa? He goes, yeah, I think Grandpa's good. Like, could you have just said, oh, yay? But no. It's always like that, just figuring out what the other person's going to say and figuring out what each other's like Christmas presents are and stuff. Anyway. It's a fun conversation, though. When you want to have a baby, it's totally fun to have a baby. It's not as fun when you don't want it. Hey, we can publish our experiment. And then we can maybe apply for a research grant and then publish more things and get tenure. Okay. So again, that's a correct decision, but it's usually not the one you want. But at least you don't make an idiot of yourself. Okay. Then this down here is, so that's HA true, reject HO. That's a type 1 error. That is rejecting a null hypothesis that is true. Then we got a type 2 error, which is do not reject HO, but HA is true. That's failing to reject a false null hypothesis. And of course, we got this one here. Correct decision. There's a difference, and we find the difference. And of course, that's what we want. That's what we want to happen. Okay, questions so far? Everybody's following the logic of this, because this is really just logic. There's no math here. Well, there's some numbers, I would call them I'm going to pause for a second. I want to see if there's any questions, because I've got to make sure you're okay with this. Okay. I think you're okay. I know you've all seen these things before. By the way, the book, I think, has this, one of these is different. So if you ever have to fill one of these out on a test or a quiz or something like that, I'm not saying you're going to, I'm saying that if this shows up, please read the damn thing. Don't just try to memorize what the four corners are. I set mine up like this because, you know why? Because that's when I was taught this, it looked like that. It's the only reason. It's not right or wrong to do it like this. You can put HA here and HO here, it doesn't matter. And then these all have to move. But I remember, I think our book does it a little bit differently than this. I think it has, something's flipped here. And I've had people say, you're trying to trick me. No, I'm really not. You should learn to read. So just read questions, right? It's really important. Okay. So again, this all makes sense. And I know like I said, I know you've seen it before, but don't feel bad about asking questions because for some of you it's been quite a while. Or frankly, for some of you it was last term. Who cares? Do you have any questions? Okay, so I'm going to move on. Next slide. So we do have some control. We set the probability of type 1 error at 0.05. That's something we do, right? All the math is based on we say what the probability of a type 1 error is, and then the rest of the calculations kind of fall out of that. And that's called alpha. The probability of making a type 1 error is called alpha. The probability of making a type 2 error is dependent, so we set this. We just say 0.05. We could say 0.0639443. That would also be fine. We don't have tables for those, but you could do that. Now, the probability of a type 2 error depends on alpha. It depends on the type 1 error. It also depends on the number of subjects and the standard deviation of the population. So why? This is because of the person who, well, we're not there yet, sorry. So 1 minus b, or minus beta rather, is a correct rejection. That's that bottom right corner in the decision matrix that I had on the last slide. That's called your statistical power. That's a correct rejection. The probability of a correct rejection. So the probability of correctly rejecting a false null hypothesis. It's interesting because we want this. We really want to reject false null hypotheses. That's because then we find effects and we can write papers and get jobs. The downside here is that we can't set this. We can guess it. There is a lecture in 2 weeks that's the hardest one in the whole course. It's about power. Power's hard because you have to think backwards. Don't miss the power lecture, okay? There's one you don't want to miss. Don't miss any of them. But the power one's really, you really probably need to be there to ask questions. So that's the probability of correct rejection, or power. So we have some control, but as you asked, 0.05. What do we set alpha at? 0.05. Everybody else should go 0.05. It's 0.05. And the question why is a good one. This is simply because of one man. One guy named R.A. Fisher said, I don't know, 0.05 is good. You know what's called an F-test? Named after Fisher. Fisher invented the analysis of variance. Fisher invented most of the research designs that we talk about. We talk about things like a design that has between variables and within variables. We'll get there, don't worry. It's actually called a split plot, and that's because he worked on plots of land. He's a biologist. Also, he was a really flaming racist, like a horrible, horrible, horrible racist. He did math though, but he was a horrible racist. I didn't mean horrible even for his day. Like people went, dude, it's 1923, but come on, right? That was always like when ISIS said stuff, and Al Qaeda would be like, come on, guys, it's a little intense. It's like, when Al Qaeda goes, dudes, calm down. I think you're probably on the wrong side of history. That's all I'm saying. So this is all because of Fisher. And how did it work? Fisher develops this thing called analysis of variance. And he's looking at a distribution that, of course, we're going to talk about, called the F distribution. So he's talking about the F distribution, gets published, people are all excited, and he gets a telegram, because there's no email. So he gets a telegram. And this is from, was it from Tukey? I think it was from Tukey. And he's like, so you're working on this distribution. What percentage points are you working with? And the thing is, you know all those tables, like the F table, the T table, the Z table? Some graduate student, years ago, 150 years ago, did all those calculations to figure out those probabilities by hand for you. So you thank unnamed graduate student every time you do statistics, because some poor bastard did the calculus for you. So you have to do it. So he talks to Fisher and says, what are you guys working on? He goes, 0.05. I'll have my students work on 0.05 too. We'll get this whole thing done. So we just chose 0.05. Literally, that's why it happened. It is arbitrary. It is stupid. There are more and more people like me saying this, but I'll tell you, inertia is a thing. Things move slowly. So every time when I'm reviewing an article for a journal, and they show something and it says 0.0, and it's like 0.06, yet it fits with their hypotheses, I usually say, go look about that too. Go ahead. It all worked. It all's going in the same direction. Let the reader decide how important the probability of a type 1 error is, rather than you telling me how important it is. That's my view. It's still a minority view. You will hear, by the way, you know who thinks these things? All the profs who teach stats everywhere. You know who does it? The people who don't. And go, no, 0.05, 0.05. And those people... We might want to be a little more flexible. In fact, we should be more flexible. Like, okay, let's think about some examples. Well, I mean, first of all, I actually literally had this said to me once. A editor of a journal, I wrote a paper, because that's what we do, and I submitted it for publication, because that's what we do. And because I'm not a lying sack of shit, I didn't say P was less than 0.05 at one point, I said less than 0.0504, because that's what it came out to. SPSS gave me the probability. And then I talked about this interpretation of these data. And then I was told, do not discuss non-significant effects. Oh, I see. So 0.05 is fine. But if I went over 4/10,000ths of a percentage point, oh no! You're worse than Hitler. Okay, he didn't say that. I'm clearly exaggerating. My daughter had 2 PhD advisors. The other one, that was his PhD advisor, said that. Academia is kind of incestuous. Like we all kind of know each other. Okay, let's think of an example. Where's an example where you'd want to use, let's say, 0.01 or 0.001? Like you want to be really careful. So you're going to miss some stuff. You're going to make some type 2 errors. You're going to miss some stuff. When would you say 0.001 or 0.01? What would you think? What kind of research question? So what I'm saying is, when are you going to be more conservative statistically? When would you want to be more conservative statistically? What if you're blowing the... Oh, please. Shut up.
Maybe if you're doing like drug trials or something?
Drug trials, maybe. If you've got a drug that's a really good drug that already works and has no side effects, and it's not very expensive, then who cares if this other one works? Maybe it really does. Maybe it's great. Yeah, that's a possibility. Sure, please.
Research?
Which?
Cancer research?
I don't know, but well, the problem with cancer research is life and death, eh? So if you screw up somebody's, like if you say, this works, yay! Yeah, so maybe in that case, yeah, maybe. That's not a bad point. That's not a bad point. So you want to be a little more conservative. Sure, because we have some treatments, and if your new treatment isn't going to be a whole lot better than anything else, you want to make sure that it's worth it, especially if it's got a lot of side effects, let's say, right? Because some anti-cancer meds are really unpleasant for people, and so maybe this has big side effects, but it also works it looks like it's going to work just as well as anything else. Let's be really careful here. What about just saying there's psychics or UFOs? Right? Something would just make all our understanding of the universe wrong. Right? It seems to me, if you're going to go out and say there's psychics, you better be pretty damn sure, because you're about to make a complete ass of yourself in print. Because there aren't any. Let me just tell you. Any other ideas? Thoughts? Okay. What do we want to be more liberal? Just say we don't care about type 1 errors. We're gonna make mistakes, or type 2 errors. Or sorry, yeah, type 1 errors. We're gonna make mistakes. We don't care. What about testing our water, our drinking water? Right? I don't mind there being false positives. So if they say boil your water because it's infected with something right now, yes, that's fine. So I have to have this horrible thing of now and then to drink water, I have to boil it. By the way, most of you haven't lived like that. I lived in Newfoundland where people live like that all the time. So every spring we have to boil our water for about 6 weeks, or you had to get a really good filtration system put in your house, which we mentioned. But Giardia was pretty common there, which is a disease that like a parasite, and it comes from beaver poo. It's called beaver fever, people call it. It's really unpleasant if you're any of us. If you're really young or really old, you can die. And the way you die is you poop yourself to death. Like, it's not pleasant, okay? So every year, I remember I asked the person we were testing the water, I said, so what do you guys use for like an alpha level? The guy's like 0.15, because the inconvenience of maybe we're wrong and you have to boil your water is better than shitting yourself to death. It's like, yep, 100%. I would go to 0.2. Like, I had no problem with that. So 0.15 is basically just one standard deviation. A little under one standard deviation, or sorry, a little over one standard deviation away. Right. We would never use that alpha level in a pure science sort of situation, but there we have an applied situation and one where it makes complete sense to be extra careful. Right? Nobody's ever found that secondhand smoke less than 0.05 causes cancer. Except it always goes in the same direction, yeah, it causes cancer. It's just never 0.05. Who cares? Can you come up with a theory where it's actually good for you? No. Can you come up with an idea where it can be neutral? It's probably bad for you. Let's just not smoke inside. Everything will be fine. Except all the other, the world burning. But at least we don't have cancer while the world burns. Right? So we should be flexible. We typically aren't. It's hard to be flexible when all the people out there in the world don't want you to be. You've got to end up... Usually, you end up talking about non-significant effects or things like that when you've already talked about a bunch of other stuff, and you can say, well, this didn't work, but look, it's all going to the same. Like, if you can justify it in paper, that's typically what people do now. The 0.05 thing is annoying, and it's... Psychology's laughed at for this, by the way. Like, statisticians think we're stupid for this. And they're right. We should be flexible. There's nothing magic about 5%. It's just that we like number 5. We could have chosen 4 or 6. Wouldn't have changed anything, except I wouldn't have been told don't discuss non-significant effects at 0.05 or 4. So these are, I think, and it's an important point, I think, that we have to be flexible, and we aren't flexible enough. And I'm going to tell you that next year, when you're doing your honors thesis, your supervisor will not be flexible unless it's me or Paul. Maybe Dwayne. So maybe. And that's simply, typically. I mean, and you'd probably also have something already. But I remember I've been in arguments with my colleagues. We have arguments. They're fun, pleasant arguments. We all like each other. Except for Paul. I don't like Paul very much. And I have a bit of a problem with Keo, but that's we all do, really. Joke. It's a joke. Except the part about Dwayne. None of us really like Dwayne very much. All right. Questions about this material, about this stuff? I know you've all ran into this before. So you might feel, I shouldn't ask a question. I'm going to look stupid. Don't worry about that, please. You don't look stupid when you ask questions. You look smart when you ask questions because you have the guts to get your freaking hand up. But if you don't ask any questions, it doesn't mean you're all cowards. Well, maybe you guys. You're all a bunch of cowards. You good? Okay, we're done. I'll see you next time. And we will take these up next time. We'll get our whatever our next thing is. We'll do that.
The textbook flips the rejected don't recommend.
Oh, that's what they do?
Yeah.
Okay, there it is. Yeah, yeah. Because I remember I've had.
I had to look because I knew I had it on there.
No, a couple of times I've had students say, "You're trying to trick us." It's like, no, I learned it like that. Actually,
It makes
more
more
sense. Thank you. I think it does too. But it really doesn't. It's completely arbitrary. What makes more sense? It's whatever I feel. You know. Where am I going here? I got to do that.